So let's start off with this concept called rationalize the denominator. Who has an iPhone? 1, 2, 3, 4. More than half of us. A lot more than half, actually. The iPhone calculator is awful. The app that comes with it is awful. Let me tell you why. Because if I wanted to do something like calculate the square root of 3, if I want that number, then in the iPhone calculator app, I have to type 3 square root backwards. And it is this exact problem. This is somewhat common. It's more common in Europe. It's called reverse Polish notation. It's common on old HP calculators. No one does it anymore. I mean, if we want to talk about 2 plus 3, we just say 2 plus 3. But reverse Polish notation would say you have plus, and what are the numbers? They are 2 and 3. And so it's extremely awkward and unintuitive. Well, if we were to, so you can get by on your iPhone's calculator with, if I needed to compute this, I can type this here. But what if it was in the denominator? What if instead I said, use your calculator to compute, use your iPhone calculator to compute, 2 plus. I'm sure you can add 2 and 3 and get 5, but 2 plus 3 over square root of 3, it would be harder to do. I mean, I guess I don't even need this up here. I could just say 1 over the square root of 3. Because if you enter some stuff in here, 1 divided by, you can't type the square root of 3 like that, because it would need, well, 1 won't work. I'd have to have at least 2. You have to somehow enter in this 3 and then press the square root button, and it just isn't working on an iPhone calculator. So what we can do to make it into something that we can compute on one of those types of calculators is rationalize the denominator. Now, this square root of 3 is an irrational number. What does that mean? Rational has its root word ratio. What is a ratio? A fraction. And a genuine fraction, we mean that the numerator and denominator are integers. So otherwise, people still say fraction, even though when we say fraction, we really mean the numerator and denominator are integers. So technically, a rational number is a number that can be written as a ratio of 2 integers. This is what I mean to say. A rational number is merely a ratio of 2 integers. So it would be a fraction whose numerator and denominator are both integers. Well, square root of 3 is not an integer, so that's not a rational number, this 2 over root 3. And And what's making it be irrational is specifically the root 3, the denominator. So we can rationalize this denominator. So then that way, it would be a lot simpler in a device like an iPhone calculator. So how would I do it? Well, you know, in our bag of tricks here in algebra, we don't have this huge collection of tricks. We're always either doing something like multiplying by 1 or adding a 0. That's pretty much always the strategy. We can multiply by 1 right here, but we get to choose what that 1 looks like. So I will multiply by 1 in this form. There, it's the same number. It's the same as it was before, but what does my denominator become? 3. Right? Because it's 3 to the 1/2 times 3 to the 1/2, so that's 3 to the 1/2 plus 1/2. And my numerator is the one that now has the radical. And then if I wanted to do it like, let's say, in my iPhone calculator, then I could first compute the square root of 3. I just do 3 and then square root, and it's right there on the screen. And then I could multiply by 2/3. And there I have 2 divided by the square root of 3 in a device that does not lend itself to having that done easily. My algebra professor would say that it's impolite. It would be impolite to leave the answer in this form. If I was doing some work and I got this as my answer, well, it's like shoddy, not shoddy, but sloppy. You wouldn't want to leave the answer with a radical in the denominator. Of course, in higher level math courses, no one cares anymore. It's pretty much algebra where we care about having that radical exclusively in the numerator. And it's probably just for the idea that if the radical is in the numerator, well, then you can pull it out and say that I'm talking about root 3, but I only want 2/3 of it. And I believe that that's the whole point of trying to rationalize the denominator. Instead of having an integer divided by an irrational number, I'm taking my irrational number 3 and scaling it to be 66.6666% of what it was. Here's an example. What am I going to multiply by? I want to rationalize the denominator. Square root of 2 over square root of 2. All right. What's it equal? Okay, which is? You need to combine both of your ideas. It's the square root of 2. It's the square root of 2 because you have 2 root 2 over 2, and this part here is a 1. So it just says 1 times root 2. You would do the same thing here, right? Square root of 3 over square root of 3. And what's it going to equal? Square root of 3. Can we, so there's nothing happening special with 2 or 3, right? It's going to pay for us to realize that a over root a is equal to just root A. Because I'm going to end up multiplying by root A over root A. So it was no surprise, after the fact, it's no surprise that 2 over root 2 just becomes root 2, and 3 over root 3 becomes root 3, because that's going to happen no matter what the numbers were. You know, it's 5 over root 5 will just be root 5. And that can be a very useful fact. What if in our denominator there's not just a radical, but there is also something being added to it? What do you think you could do here that would leave you with no radical in the denominator? So think about what we did on the last 2 questions of last week's homework. So those last 2 questions of last week's homework were filled with radicals. I mean, square root of 13 minus square root of 15 times square root of 13 plus square root of 15. And we decided that this was, the answer was immediate. What is the answer? -2, because it's 13 minus 15. Well, isn't -2 an integer? -2 is an integer. It's rational. But right here there's an irrational involved. Over here I have a rational number, and in your denominator right there you have something looking like this. Do we agree with the example here at the bottom, everyone? Then what if the example I had up here was 1 over the square root of 13 plus the square root of 15? What could you do? You can only multiply by 1. There's no other choice. What could you do to make it so that the denominator didn't have an irrational anymore? It already has a plus. Minus. You should purposely introduce the conjugate of this denominator. So you're going to multiply by 1 in the form of the conjugate of the denominator over itself. Because by the difference of 2 squares property, that denominator will become an integer. It won't be irrational anymore. It'll be a rational number. And we get just whatever we get. Root 13 minus root 15 in the top. In the bottom, we now have -2. The denominator has been rationalized. Now extend this idea to the one that I was looking at. multiply by 1 in the form of yeah, it's merely the conjugate of the denominator. And what is that new denominator? Negative 1. It says 1 minus 2. Yeah, negative 1. And the numerator is just 1 minus root 2. Can we write that so that it doesn't look like a fraction? And has no parentheses? And does not have a dangling minus out front? And what would you say then? That has a dangling minus out front. Just, yeah, switch their order. This is root 2 minus 1. Didn't we talk about that in week, I think 5, where they had a bunch of stuff for you to factor, and it would be like x minus 1 up here, and then 1 minus x down here. And I had to convince you that this said x minus 1 over negative x minus 1. It's that idea. And while it's certainly true that this is minus 1 plus root 2, this has more symbols and has that dangling minus hanging out front. So if there's an opportunity to have less notation, take it. It's not absolutely required, but to me it's uncomfortable to have that minus. Like if I can avoid having that minus at the very first term, I'm going to try to. We know what we would do here. We'd still multiply by root 2 over root 2. But I want to argue that we're multiplying by the conjugate of the denominator over itself, which is the very same thing we just did in the other problem that had the sum. Because this, if I put in a bunch of extra stuff that doesn't need to be there, would say this. Then I can multiply by the conjugate of that denominator over itself. And so then the realization is that there's not two methods, right? We don't do this one thing when it doesn't have a sum and then do this other thing when it's two things being added. It's the same method where if there's nothing being added, then the conjugate, then it equals its own conjugate because you're just adding and subtracting 0. And what does this come out to be? I mean, all of this writing is for decoration. If it's in your way, you can ignore it. You would just be multiplying by the square root of 2 over the square root of 2. Or if you paid careful attention to it, then that denominator would become 2. Yeah. And the numerator would just be, okay. Let's do some of the problems. 10 over the square root of 2. So what if I wrote that like this? It's still the same number, right? But immediately you know what 2 over root 2 is. It's square root of 2. 2 over root 2 is just the square root of 2 because it's that rule, it's that useful fact, a over root a is just root a. So the answer here would just be 5 root 2. Maybe you don't remember that fact and go ahead and try to solve it in the normal way. So then you'd have 10 over root 2 times root 2 over root 2. You'd be getting 10 root 2 up here and then a 2 in the denominator. So 10 divided by 2 then would be 5 root 2. Either way it gets it done. Minus 7 over root 12. Can root 12 be simplified? Did I say root 12? I meant root 12. Can root 12 be simplified? Yeah. What is it? Okay, and what's square root of 4? So square root of 12 is 2 root 3. This thing that we're looking at says minus 7 over 2 root 3. If there's an opportunity for you to simplify that radical first, I would encourage you to do so. Because there'd be no reason for us to be going around multiplying by big numbers. Or trying to do something if we had just left it as square root of 12, we'd be getting minus 7 over 12 times root 12. And I would still have to simplify that root 12, right? So we might as well do it first, and then it'll make things simpler from the outset. Because this is, you don't have to view it from this perspective, but I will. It's minus 7 over 2 times 1 over root 3. So now the problem has changed into, I've got this fraction, minus 7 over 2, and then the thing I'm wanting to rationalize is just the 1 over root 3. And it's going to be, I guess we should have covered that useful fact. Also, there's a corresponding useful fact. 1 over root a is going to be, I don't know, let's see. So I'd be multiplying by root a over root a. You're going to get root a over a. So something like 1 over root 3, you can immediately recognize would become root 3 over 3. So then I can see that this should be minus 7 over 2 times root 3 over 3. And so my final answer would be minus 7 over 6 times root 3. Or you can put the root 3 in the numerator, it doesn't matter. do you think? All right. I guess there's some other stuff I forgot to tell you. So the square root is, it may seem like a weird place to have this word, but it is a linear operator. So that means the square root of the product is the product of the roots. It behaves very nicely in this way, just like you would expect it to. Then, correspondingly, if well, we talked about that last week, so you already knew that. But building on this fact, then, if that number A is really some something with a denominator, then the thing we would have started with would look like this. And then applying that same rule, it would be looking like this. And the 1 over d is like this with an exponent. But if I'm taking the square root and using just exponents, then I would have that. So evidently, something that's the square root, and it has a denominator like that, could just be so it's got a 1 in the numerator. That's important because I end up being able to write it just as d to the negative 1, which would simplify to d to the minus 1/2. Then you just turn right back around and say that this is just 1 over the square root of d. The point is that the radical symbol, here it's around the whole, here it's around both the numerator and the denominator. But somehow magically it just gets around the denominator. Then the point is you end up with this. So it's analogous to what happens in multiplication. And it should be, because division is a type of multiplication. So if I have root 11 over root 5, I'm probably going to immediately view this as root 11 over root 5. The thing to multiply by is root 5 over root 5. When I compute the new numerator, is it going to simplify? No. How come?
Because square root of 11 and square root of 5 are irrational.
It's true that they're irrational, But the square root of 6 times the square root of 3 will simplify, and those are both irrational. So what's the real reason? How do I build a 6? Okay. So when these things multiply together, I'd get this, which would simplify. So then how come this one won't simplify in its numerator once I multiply it together? They're prime numbers. They're both prime numbers. 6 is not a prime number. 6 is not a prime number. If they're both, so it's not just that they're both prime, but that they are co-prime. That's probably more correct. Meaning that they don't have any common factors. They don't have any common factors. So if I had something like square root of 6 and the square root of 35, well, those aren't prime either, but their product won't simplify because 6 is 2 times 3 and 35 is 5 times 7. They're co-prime, they don't share any common factors. So when I mash it all together, I'm not going to have any pairs, right, of factors. So 5 and 11 not only are prime, but because they are single prime numbers that are different, then they are co-prime. So you would just get the square root of 55 here, and it'd be 5 in the denominator. All right, well now they have, it looks like a trickier problem. The cube root of 5 halves. And they want us to rationalize the denominator. Now up until now, we had said stuff like, multiply by the conjugate, multiply by 1 in such and such form. But when we were doing that, the index was always 2. Now it's 3. What should I do? What's the question mark here? Cube root of what is 2? Huh? 8. Because 2 times 2 times 2 is 8. It's simplifying to become a 2 because there's a trio of 2s. If my index was 4, I'd need a quadruplet. I need 4 of them. Okay? So, in that denominator of the problem, we just have the 1, 2. There's just one of them. So I can't just put one more on there. It won't become rational. How many more do I need? We said that this thing down here at the bottom simplifies. What's different about this thing at the bottom and that denominator up there? What would you say if I wasn't making all this big deal about it and I just said, here, get started, and you just tried something? What would you try? In the same spirit as the problems we've been doing, what would you try? Okay, so here's the denominator, it's cube root of 2. So we're going to multiply by 1 in the form of cube root of 2 over cube root of 2. Let's see what happens. You have now this part. Is that going to leave us with a denominator that's rational? No. So what do I need? Another one. You need 3 of them because it's index 3. Index 3, I need 3 of those cube root of 2s. If it was index 4, I'd need 4 of those cube root of 2, 4th root of 2s. Just like if it's index 2, which is the square root, I only need a pair. So here it has index 3, so I need another one. Now you can write this in a more consolidated way because this stuff that you're multiplying by is really the cube root of 4 over the cube root of 4. So alternately, you could have just realized that you were needing to say cube root of 5 times cube root of 4 over cube root of 2 times cube root of 4. Then the denominator becomes the cube root of 8, which is 2. And the numerator is the cube root of 20. Will the cube root of 20 simplify? How? Okay, so tell me what's then the problem. I think you realize why it won't simplify. Tell me why it won't. Construct for me a 20 out of prime numbers and find the triple of primes in that construction. I'm ready. What would it be? That's 20. That's its prime factorization. There is no other prime factorization besides that one. And it does not have 3 of anything. There's a pair of 2s, there's a single 5. I need 3 things in order to simplify this numerator. So like if it was the cube root of 40, we could simplify it. It'd be 2 cube root of 5. Cube root of 40 would simplify because 40 would be 2 times 2 times 2 times 5. So when you're dealing with that index being different from 2, it's just guiding you to say how many belong in your group that will collapse down. Here we needed 3 things. That's why we ended up having to multiply by the cube root of 2 and then do it again. So that way there was 3 of them. Final answer, cube root of 20 over 2. I have to go and pick this little special tool down here, the nth root tool. So that way it'll give me the box to type in my index, which is 3. And it was the cube root of 20. I have to make a fraction first, and then here we get the cube root of 20 over 2. Questions on that one? Back to where it was. What would I multiply by here? Okay. That won't leave us with a rational denominator. Let me show you why. Well, first of all, you said 8 root 5. I think it means the 5th root of 8. So the 5th root of 8 over the 5th root of 8. Here in the denominator, I'm going to get what? And how is a 64 built out of prime numbers? So once the numbers start to get big, it's unpleasant. Factor it first. 8 is what? 8 is 2 cubed. 8 is 2 cubed. So we have 2 cubed, and we have the 5th root of it, and the suggestion is to multiply by, again, the 5th root of 2 cubed. How many 2's are going to be right there in that denominator? And that's one too many, isn't it? So let's back up and say not to multiply by the 5th root of 8 over the 5th root of 8, because I don't need 6 2's. I only need 5 2's. So the thing to multiply by is The goal here is to have a grand total of 5 2s in the bottom. Because that is the only way that that thing is going to collapse down into an integer. Is that the index and the exponent match. This is what I would like. 5 2s. There are 3 of them sitting right there. So I need how many more? 2 more. And that's what 4 is. 4 has 2 2s. So let us multiply by the 5th root of 4. Then that denominator will collapse down. It becomes just a 2. And then 4 over 2 is 2 itself. What do I multiply by? Talk to me about 27. What is it made of? Made of 3s. It is 3 to what power? It's 3 to the 3rd power. Well, 3 to the 3rd power, that exponent of 3 is not a 4. And if I want it to simplify, it's got to be a 4. You only have 3. So you need one more, don't you? So you would multiply by 1 in the form of what? Over what? The 4th root of 3 over the 4th root of 3. It's got to work because now we get just whatever we get in the numerator, but down in the denominator, since 27 was 3 to the 3rd power, and I'm multiplying it by another 3, you have 4 of these 3's in the denominator now. So it will simplify because the exponent and the index match. That is the whole gimmick. So that denominator just becomes a 3. This is the 4th root of 3 over 3. I good to go to the next one?
Yeah.
I'm waiting on y'all. Ideas? The pain will continue until we understand how this problem goes. So y'all got to tell me how to solve these, couple in a row, and then I'll quit doing them. And until then, I'll just spend the entire rest of the day. I don't care. I can pay the same. Y'all will get behind. I know y'all know how to do this by now. What do I multiply by? Say it again. The third root of 25. You multiply by the third root of 25 over the third root of 25. Tell me why. You needed 3 of them. Okay. And what does this denominator become? 5. And you're left with whatever you're left with up here. Seven over 6 plus root 3. How did we get that one done?
We have to multiply by the conjugate.
Conjugate of the denominator over itself. That is
6 minus square root 3.
And what does the product of that denominator and its conjugate become? It's a difference of 2 squares. It's a difference of 2 squares, so yeah, 33. Because you would get 6 squared minus root 3 squared. So this denominator is 33, and the numerator is just whatever you get, 7 times 6 minus root 3. And there's no need to distribute it in, but you certainly could. It would still count it right. Or you could even say 7/33 of this thing in parentheses. You know, it's 10 of 6 of one, half a dozen of another. All right, let's take a break. They want to ask us several more of this style of question, and then it continues to use radicals, but it switches gears a little bit because we want to try and creep up on this derivation of the quadratic formula. Everyone's favorite formula from algebra. And, like I said earlier, Justina will not let me forget to talk about the discussion board, because it's a handy tool that we get out of it. All right, let's take our break. 7:07, so we'll come back 7:17.
It was yeah, it's so that's why I was like this type of it's it literally breaks it down. Yeah, it breaks down. That's how I was able to understand it. Yeah. The boys are here. It makes it so much easier, and I don't need to know. I know they just yes.
Oh, wow.
About if I know this
Yes. I'm gonna say now it's changed.
been working on it over here. Trying to stay up.
Alright, I'm back. I'm gonna go waste my money and my time.
I told you. I've been trying to write it down this hard. I don't know if I'm going to fail, but it's what it is. Yeah. Yeah, I'm gonna have to listen to it again.
Honestly, it's just this guy. He sounds but specifically, but specifically that character for me because he's so dry. He doesn't get like.
I have to see.
How'd you compute that? It's a squared minus b squared. Now what is a? In your problem there, what is the a? A is 4. So you have to compute 4 squared. Now what is the B? And so you'd have to compute the square root of 3 squared. What is the square root of 3 squared? So the square root of 3 is just 3 to the 1/2 power. And then you're going to square it. Okay, that's the square root of 3. Now square it. Times itself. Linda, remember this example? Square root of 2 times the square root of 2, look what we get. Square root of 3 times the square root of 3 is just 3. minus 3. That's your denominator. Rosalinda, you're going to help me do this one. Okay. So Rosalinda is going to help me do this one. You can tell me what we would multiply by. 1 in the form of there's already a plus here.
Square root 3. Square root 3.
And what's the symbol that goes between them?
It's a minus.
It's a minus. You have now purposefully produced this conjugate pair in the denominator. You can tell me, are you watching? Rosalinda, you can tell me what this would compute to be now without writing anything down. What is root 5 plus root 3 times root 5 minus root 3? It's 2. The denominator is 2, and the numerator is whatever we get. In this case, 4 times root 5 minus root 3. The 4 and the 2 cancel, so this just becomes 2 times root 5 minus root 3. That's as far as you can go. You could distribute it if you want, doesn't matter. I'm going to multiply by 1. And what does that 1 have for its numerator and denominator? Go back. Got it? Okay. Someone will tell me what I should multiply by. It is the conjugate, and what would that be? 4 plus root 3. And what number do I get now in the denominator? This thing has the form of a minus b times a plus b. We know that that is equal to a squared minus b squared. For you to compute the answer, you need to identify a and identify b. Square them and take their difference. 13. How is that computed? So it's 16 minus 3. That is a squared minus b squared. And in the numerator, you get whatever you get. They are asking me to simplify my answer. Is this, if I wrote that denominator as 13, would it be simplified? Would all of the radicals be made as small as they can? What about root 12? No. In fact, root 12 is what? Root 12 is 2 root 3, because you have square root of 4 times the square root of 3. So, that 2 root 3, if we were to distribute it in, we're going to get another simplification. What does the numerator now look like? Once I distribute it in, what will it say? 8 root 3 plus 6. And it's over 13. Now it's as simple as it could get. There's only one radical now. Is yet another simplification, instead of having 2 of them, like we did up here. And how come we got 6? Uh-huh.
And 3 times 2 is 6.
Very good. So when I distribute this 2 root 3n to the root 3, it winds up saying 2 times 3. All right, good on this one? In fact, number 1 here, I'm taking the square root of something and then squaring it. And it winds up just being just this x. Roslinda, this would be like the square root of 3 times the square root of 3. It's just 3. But if I switch the order of the squared and the square root, well, that's more delicate. This one has to just be x because the x already must be non-negative. Because we can't be taking the square root of a negative number and have it be real. It would be complex. So since it's already either positive or 0, then when I square it, I don't have to worry about these absolute value bars. But down here, you could take a number like -3 and put it in for x. I could take -3 and square it, and I'd get 9. And then the square root of 9 would just be 3. And that's why I'd need these absolute value bars. It wouldn't be -3, it would be +3. So the absolute value of -3 is just 3. That's the example I just told you about. Now this fact number 2 is important for what we'll do here in a moment. So the next several problems, we use fact 1, and then after that we use fact 2. So detect when that change is going to, detect when that change has happened, and adhere to the very important, the square root of something squared is the absolute value of that something. In fact, it is the definition of absolute value. It is an alternate definition from what you may have seen. Here I have the square root of something equals 1. Now I know 2 things when I'm dealing with square roots. First of all, the thing under the radical is not negative. Also, the square root of that thing is not negative. That's why it's equal to 1. So it's a perfectly valid equation. It's equal to this non-negative number, so this equation makes sense. Let us square both sides. If I square both sides, then we are using fact number 1 from the previous screen. And so I had the square root of something, then I square it, it just kind of deletes the square root symbol. It's just like how the square root of 3, and then you square it, it just comes out 3. You didn't never have to worry about a negative being in here in the first place. So when you square both sides, you wind up with just this linear equation, 8x minus 9 equals 1. And so x is equal to I would add 9 on both sides. If I added 9 on both sides, how would it read? That's what x is equal to. If I add 9 on both sides, it'd say 8x is 10. And once you're there, you just divide by 8. So if 8x equals 10, then x must be 10 over 8. Now, can I type 10 over 8 in the box and have it take it? No. Because 10 is 2 times 5, and 8's 2 times 4, and these 2's cancel. All right. It's asking me for the solution set. That means the collection of numbers that satisfy the equation. Don't give it another equation here. It just wants the numbers. And remind me what this weird looking symbol down here is. It's a circle with a diagonal line through it. Huh? If there's no solution, then what is in my solution set? No, that would be there's a bunch of solutions, right? So you kind of, you know, if I didn't, so if there was no solution, then there wouldn't even be a number in here, right? How many things would be in there? If I took this 5/4 out. So right now there's one thing in there, the 5/4. Take it out, then there's how many things? Nothing. There's no items in it. So then this would be equal to these curly braces with nothing inside. It is the empty set. It's a collection of no objects. And it's looking like a glorified 0. And you can, I guess, remember that it's the set that has 0 objects in it. Let's look at this equation. X equals x plus 1. Does it make sense? Uh-huh. So then what would your new equation say?
Equals plus 1.
What equals 1? 0. 0 equals 1. It's a contradiction, right? So I can write this. There's nothing wrong with me writing it, but there's no solution to this equation. In fact, it proclaims that 0 is 1. So that's not true. This has no solution. What's going on over here then? You can either start doing your algebra until you see a problem, or maybe you just keep on doing your algebra and all the way to the end and get an answer, type it in and get it wrong because you never noticed the problem. Three is positive, right? 3 plus some number is 0. But what do you know about this other number over here, the square root of x plus 9? It can't be negative. So right now this is saying 3 plus a number that can't be negative is 0. Is that going to work?
No.
Oh no. So our answer is
B.
B. There's no solution. The solution set is empty. So you could move, like suppose you never noticed there was a problem, right? You would get the square root of x plus 9 equals minus 3. You'd square both sides. You get x plus 9 equals 9, right? Because minus 3 times minus 3 is 9. So then you'd try and say, well, I think x is 0. You could put it back in and check real quick. It would say the square root of 9 plus 3 equal to 0. So that could be a fail-safe, right, to keep you from getting the wrong answer. So what is happening is when we square both sides, we introduce what's called an extraneous solution. So I can go through all these valid algebra steps, but even if all of my steps are perfectly valid, if I start with something that is a contradiction, I can show anything I want. I can show you that 0 equals 1, like we did in that example a minute ago. And right here, the thing I'm pointing to is the problem. That this can't actually happen. So then everything valid that I do afterwards is pointless. And the answer I get at the end is meaningless, right? And you can see that it didn't work when we substitute it back in. The square root of the left side equals the square root of the okay. So they're square rooted on both sides, right? I guess what I'm trying to say is if the square root of A equals the square root of B, then it would follow what? What do you think I'm going to write? A equals B. It's just got to be the case, right? If I have the square root of 9 equals the square root of 3 squared, then, or if I had the square root of 9 equals the square root of 4 plus 5, those are the same. So it's got to be the case that 9 is 4 plus 5. Okay, so square roots on both sides let's just ditch them. This would give to us 7y plus 5 equals 6y plus 6. Move the 6y to the other side. Move the 5 to the other side. So you have y is equal to 6 minus 5, 1. And you can check it. That's easy enough. It's always easy to check when the solution is 1. So it would be 7 plus 5. Is that equal to square root of 6 plus 6? Sure enough. So I'm just going to take the square root on both sides, right? And that's what seems right. I mean, we had square roots a minute ago. It was equal to something, and we squared both sides. Now it's this thing squared, so I'll square root on both sides. Okay. And what's the square root of 49? 7. And what's the square root of the left side? You want to do x minus 2? Is that it? Okay, what should it be? Absolute value. I gotta consider the absolute value when I'm taking the square root of something squared. If I have the absolute value of a number, then I need to consider the positive version and the negative version. So this will result in two answers. We will have the answer for which x minus 2 equals 7, not x plus 2. X plus 2 is the conjugate of this. How about 2 minus x equals 7? Yeah. Because 2 minus x is the negative of x minus 2. So we would have x minus 2 is 7, or, let me write it like this, negative of x minus 2 is 7. There you can plainly see that one of them's positive, the other one's negative. And even if I took all of this right here and put it back into the absolute values and computed it, I would get x minus 2. So I have both the positive version and the negative version. So it's going to be x is 9. And then this side would be 2 minus x, negative 5. And you get two solutions. You can try them both. Probably should. So I put the 9 in right here. It'd be 9 minus 2. That's 7. 7 squared is 49. Okay. Minus 5 minus 2. That's minus 7 squared, which is still 49. So it works. kind of curve is this thing associated with? If I wrote it like this, it's a parabola. It's a parabola. And look, I can see here by these numbers that the lowest point on this parabola is the point two and minus 49. So this parabola goes through that point. It's the vertex. Additionally, we solved this. We solved, this is a parabola. And if I move the 49 over, it would be equal to 0. A minute ago, I had it equal to y. You said it's a parabola. But if it's just equal to 0, then I'm looking for the places where the y value is 0. Well, that would be where it crosses the x-axis. And evidently, that's going to be at 9 and minus 5, where it crosses the x-axis. So over here at 9 and over here at minus 5, it will also go through those 2 points. And so the curve would be looking something like this. True or false? 2 is halfway between minus 5 and 9. True. This is called the axis of symmetry. This curve is symmetrical on either side of that dashed line. And the vertex occurs right on the axis of symmetry. Let's get this parabola in the form ax squared plus bx plus c. The regular old form of a quadratic. So I would multiply this together. I get x squared minus 4x plus 4, and then here's a minus 49. So this should be looking like x squared minus 4x, and then minus 49 plus 4, that's minus 45. Can we factor that? What are the factors? Are those numbers familiar? They're the exact numbers that we got a moment ago when we solved that thing, the original problem. When we solved this and we're careful to use our absolute value, we still got the 2 roots. So these are all equivalent. They're all the same curve. And the critical, so suppose you had started right here, right? Somebody gives you this parabola, this quadratic. Well, we know how to factor it, go this direction. I'm wondering if we can figure out how to get to this step and then back to this step so that we can go here. That process is called completing the square. I think that on your homework, they don't have any completing the square problems. If they do, maybe there's one at the very end. But then there's some on the quiz. And it's not hard. And they're both going to yield for us these numbers, -5 and 9. It's not like someone's looking over your shoulder to see which one method you're using. So even though the instructions say, do this by completing the square, they're not going to know. But it is useful to see how to do it, because this formula that you probably heard of, the quadratic formula, is born from completing the square. And it's for that reason that they have these problems here for us to look at. I claim these are the same equation. Not the same, but equivalent statements about x. And if so earlier in the problem set, we were multiplying by 1. That's something it's like what we do in algebra. Well, now I'm going to add 0. That other thing we do in algebra. I'm going to add 0 in this special way. I have my x squared. I have my -8x. But now I want to add the quantity -4 squared. If I add that, I'll turn right around and subtract it. And a -4 squared is just 16. And then I still have my +5. So these are the same. These are the same. Except for all I've done here is add 16 and then subtract 16. So I'm adding 0. And I'll tell you where I got, how I was able to choose that number in a moment. But if you look, by my judicious choice, these first 3 terms will now factor. They will factor into a perfect square. These first 3 terms say x squared minus 8x plus 16. And I've chosen to write this plus 16 in a funny way. Because the thing that those first three terms will factor into is just x minus 4. You can check. You would get x times x, that's x squared. And then x times minus 4, but then x times minus 4 again, and then minus 4 times minus 4. That's 16. So these first three terms factor into this perfect square. And then the numbers over here I'm just left with. Minus 16 plus 5. Well, that's minus 11. Add 11 to both sides, and you're at the original statement of the problem. So what I've done is called completing the square. You would be handed a polynomial like this, and it would say something like, complete the square to find the roots of the equation. And so here's my traditional looking ax squared plus bx plus c is how we'll name this, right? Where the coefficients are a, b, and c. And the only question is, how am I getting that 16? Well, there's a clue in that it's written like a minus 4 right there, because this coefficient here being minus 8, if I took half of minus 8, it would be minus 4. And that's where I got this minus 4 right here. And then I just square it. I take half of the coefficient in the middle and square it. And when you do that, without fail, the result will be that these first three terms are a perfect square. And this minus 4 is exactly that thing that's right there, the thing you squared. And then you add the 11 to both sides, and now you're at this stage of the problem where we would continue right on and solve it. So I would, yes?
Where did you get the minus 16 from?
Because I added 16 right here. I've added 16, but I want it to be the same equation, so I need to subtract 16, so that way it's net 0.
How did you get 5?
How did I get 5?
Yes.
The 5 was the original statement of the problem up here. So I knew that it would be a 5 because I just worked this out in my head, right? I said that this is going to be x squared minus 8x plus 16 minus 11 equals to 0. And I said 16 minus 11 has got to be 5. So I came up here and said, I claim that these are the same. And it turned out that they were, because all I needed to do to show you that was, so there's my x squared minus my 8x, and then half of negative 8 is negative 4. So I'm going to take that negative 4 and square it. Now that's really adding 16, so I should turn right around and subtract 16, and then I still have my 5 here. And then these first three terms will always factor down into a perfect square, like this. And then the minus 16 and the 5 is just minus 11. Okay. So now we can take a square root on both sides. If I take a square root on both sides, I would get is that really what it is over here? Just x minus 4? The absolute value of x minus 4 is equal to the square root of 11. So that's telling me that the stuff that's inside here, inside these absolute value bars, should either compute to square root of 11 or it should compute to the negative of square root of 11. So that's why we have to consider the positive version and the negative. So let me write it like this time. We would have x minus 4 equal to root 11, or x minus 4 equal to a negative root 11. Maybe it's more plain to see in this way. This one's obvious, right? You just ditch the absolute value bars. Over here, I'm saying that x minus 4 is really this negative number, negative root 11. And if I take that number, if I take that number, negative root 11, and put it inside the absolute values, the negative is gone, and it just says root 11. Okay. So that's why we must consider both of them. Well, if I just add 4 on both of these, then they form something that's kind of like a conjugate. It's 4 plus or minus root 11. Now, the 4 was not a surprise because there's a 4 right there. The vertex of this thing can be easily seen to be the point 4, comma, minus 11. If I'm just looking right here at this, right here is my x coordinate and right here is my y coordinate of the vertex. When I go and look at a graph of this guy, this would be my axis of symmetry. There's minus 11. There's my vertex, because this is at 4. And look at how on either side of that axis of symmetry, it says exactly how far you need to go. So stand at the number 4 on the x-axis. If you went to the right by square root 11, you'd be at one of the roots. Or if you were standing at 4 and you went to the left by the square root 11, you'd be at the other root. Because it's symmetric around that number 4. So you would have one of them here. You'd have the other one like right there. And this is 4 plus root 11. Over here would be 4 minus root 11, and the curve looks like this. When you go to type in your solution set, you have to give it to them in 2 answers. They don't let us get away with this plus minus. Although, I've never actually tried it. There is the button here. I'll tell you what I'm going to try. 4 plus minus root 11. See if it works. Hey, how about that? However, you could also explicitly list 2 solutions, 4 plus root 11 and 4 minus root 11. That's what I always did in the past. we did all that because here in problems 13, 14, and 15, they're wanting to talk to you about this quadratic formula. And it's extremely difficult to appreciate the quadratic formula in the absence of understanding about completing the square. So let's take a break, and when we come back, we'll do these last three problems. See how the quadratic formula just pops into existence by completing the square, and then call it a day.
Oh no, I'm not. I did it. I'm breaking my brain.
You both know.
Oh man, 75. You should try to do this. Wow. I was like, what? The crap?
I'm sorry, I'm not good.
My ex. No, 82. Still got homework and discussions I can add to that. So, man, I was just like, I'm like, it just depends.
No, where's your work at that you just did?
This one.
Yeah, where's the work? Show me on the paper. Why would you do it again if you already did it? You understand what I'm saying? I don't see the work anymore.
Now I was facing between this one, so
Okay.
I changed the figure. This one to 5.
Okay, what's 5 squared? Hold on, what's 5 squared? Okay, 25. What's square root of 3 squared?
9.
Nope. Nine is 3 squared. 9 is 3 times 3. We're talking about the square root of 3 times the square root of 3. It can't be 9. What if I wrote, instead of writing square root of 3, I wrote 3 to the power of 1/2? And then that gets times 3 to the power of 1/2.
It should be a 6.
No, it's not. 6 is 2 times 3. 3 to the 1/2 power times 3 to the 1/2 power. Okay, you have exponents. You have this thing times this thing, those exponents need to be added. What's a 1/2 plus a 1/2? It would be 3. The square root of 3 squared is just 3. Now, you said that 5 squared is 25, and square root of 3 squared is 3. So 25 minus 3. That's the denominator. Okay? The numerator, you have it. No. Yes, sorry. 25 minus 3. 22. All right, here's my quadratic. Can we factor this? Like, you remember that technique that we had used? A times b would be minus 36, and a plus b would be negative 5. So then we know that the solutions to if this thing was equal to 0, the solutions would be negative 9, or excuse me, 9 and 4. Because it would factor like x minus 9 and x plus 4. Okay. And so it's probably this problem where it will factor into integers. But it could have been the case that this was 37. Then it wouldn't have worked. And we would still want a strategy that made it, that allowed us to still get the factorization. So let's go, since we know how it's going to come out, let's go ahead and complete the square. So since we know how this factors, we would know that x would be either 9 or negative 4. Those are the two numbers that when I put them in, I would get 0. If I wanted to complete the square on this, all I need to do is look at this middle coefficient, the minus 5. I need half of that, and I'm going to square it. So I'll have x squared minus 5x, and then half of negative 5 squared. Now that ends up being 25 over 4. So here I've just added 25 over 4. So I need to turn around and subtract 25 over 4. And I still have my minus 36. And these are the same equation. Equivalent equation. The first three terms factor always now into a perfect square. In fact, it would say x minus 5 halves. And then you'd square it. And then you're still left with the minus 25 over 4 minus 36. Minus 36, let's see, would be negative 144 over 4. Right, just view it like this. You'd have minus 25 over 4 minus 36 times 4 over 4. So then that 36 is really just 36 times 4 over 4. And 36 times 4 is 120 plus 24. So it's 144. So this is saying minus 25 minus 144 over 4. And this thing is equal to 0 still. But when I move the 169 over 4 to the other side, then I have one of those equations like they had just given me for the last several problems. I can move that 169 over 4 to the other side, and it would say x minus 5 over 2 equal to, squared, equal to 169 over 4. Take the square root on both sides, and you end up with the absolute value of x minus 5 over 2 equal to 13 halves. Because the square root of 13 is, or because the square root of 169 is 13, square root of 4 is 2. And so I would have the positive version and the negative version. You could write it like this: x minus 5 over 2 is equal to plus or minus 13 over 2. And then we'd be at the final step where x is 5 halves plus or minus 13 halves. And 5 plus 13, that's 18. So 18 over 2. 18 over 2 is 9. But 5 minus 13 is negative 8. So negative 8 over 2. And aren't those the same solutions? Yeah. Now granted, there's an awful lot more writing that we've done here, but the benefit is that everything would have been exactly the same even if I changed that 36 to a 37. So now we would have the ability to get the roots, to get the solutions to this equation no matter if it could have been factored or not. And that's going to give us a idea about this thing called the quadratic formula. So let's try completing the square again on this one. Well, one thing I forgot to mention about completing the square is that the leading coefficient must be 1 when you do it. So this says 6x squared plus x minus 2 I'm curious if we could factor this. So a times b is negative 12, and a plus b is 1. Wouldn't 4 minus 3 do it? Yeah. So I could write this as 6x squared plus 4x minus 3x minus, well, let me do it like this. Minus 3x plus 4x minus 2, and then factor by grouping. So I'd factor out a 3x and be left with x minus 1. And then I'd factor out a 2 and be left with x minus 1. So it looks like ultimately these factors into 3x plus 2 times x minus 1. So then if this was equal to 0 the whole way, my solutions would be 1 and negative 2/3. It must be a negative 2/3 because if you put that number right here for x, the 3's would cancel and it'd say minus 2 plus 2. So, great. This still factored, but if I get to changing this up here, it won't. I can just alter this constant and suddenly it won't factor anymore. Completing the square on this one, we'd have to factor out the 6. We could certainly do it. So 6x squared plus x minus 2 if I factor out a 6 everywhere, I'd be left with x squared plus 1/6 x minus 2 over 6. That's 1/3. So it could be unpleasant with respect to these fractions because I'd have to have half of 1/6, which is 1/12. And I'm going to square it. That's 1/144th, and on and on and on. Instead of me spending the time to do this, why don't we investigate what would happen if because it's going to be the same amount of work if I complete the square on this one that has specific numbers, or if I complete the square on this one where the numbers are just whatever you want, right? A, B, and C. And if I can trace out what's going to happen when I complete the square on this one, then when I get to the very end, I can just see where A, B, and C are located. And circle back around and say, okay, well, A was 6 and B was 1 and C was negative 2, so I can just plug them in down here into this thing I get and get the answers that way. And in fact, I can just save my work. If I complete the square on this thing, I'll just save my result, and then whatever polynomial someone gives me, I can just refer to what I get down here and immediately be able to tell you what the roots are. But A a is not necessarily the number 1. So in order to complete the square, the first thing I would have to do is factor out that a. You do not need to write any of this stuff down. Just try and follow along for a moment. So I factored out my a. Now I'm looking at b over a and c over a, and fractions, I'm sure you would agree, can be unpleasant. Let me make the substitution of a p and a q. I want to consider now x squared plus px plus q. And we're going to complete the square on this thing, where p is just b over a and q is just c over a. I want half of that term in the middle, a half of the p, and then square it. Now that I've added p squared over 4, I should subtract p squared over 4, and I still have my plus q. It's the same equation. But now these first 3 terms will factor into a perfect square. In fact, it will say x plus p over 2, and then it's squared. And I'm left with just minus p squared over 4 plus q, whatever that is. Now, if this thing was equal to 0, then I could move the minus p squared over 4 and the q to the other side. And it would say x plus p over 2, and you square it. And it would be equal to a positive p squared over 4 minus q. Take the square root on both sides. You would get your absolute value. That immediately translates into the positive version and the negative version. So it would look like x plus p over 2 is equal to the positive version and the negative version of the square root p squared over 4 minus q. Well, only one more thing and it's solve for x. That's to move the p over 2 to the other side. So x must be equal to minus p over 2 plus or minus the square root p squared over 4 minus q. This is the quadratic formula. It's just hidden a little bit from the usual writing. All I did was I factored out that a, so that way this is a b over a and this is a c over a. And then I completed the square on the result here, and we have the solutions for x. Well, if I use that right there, but now that I'm done with the hard part, I'll put the b over a and c over a back in. This is what we ended up with, but p is b over a. In fact, let me write this minus p over 2 like this. It's really minus p times 1/2. This p squared over 4 can really be thought of as p squared times 1/4. Now p was b over a. So if I replace that p right there with b over a, I would have a minus b over a times 2. if I replace this p right here with b over a, you would say b squared over a squared. So here I'd have my square root, and I'd have b squared over a squared, but then it's times 4. So it's 4a squared right there. And q was c over a. So then it's minus c over a. Now you just make one little factorization in the bottom here, and you would have it in the traditional format. So I will factor out here a 1 over 4a squared. From this terms, I'll factor out a 1 over 4a squared. So the first term will just say b squared. Now, if I'm pulling out a 1 over 4a squared from here, then it doesn't have a 4a squared here in the bottom. It's just got an a. But I can make it look like it has a 4a squared down there. I'll just multiply by 4a over 4a. Now it does have that 4a squared in the bottom, so then when I factor it out, I'm just left with a 4ac in that numerator. And then how does this thing right here simplify? One over the square root of 4a squared. I did all the rest. Y'all can do this part. What is the square root of 1 over 4a squared? It's 1 over 2a. It should really be the absolute value of 2a, but we're off the hook because it already has the positive version and the negative version. So you just get 1 over 2a right there. And people will usually write that 1 over 2a just kind of down here. And there it is. This is the result of completing the square on this thing. So then if I have a 6x squared plus x minus 2, then a is 6, and b is 1, and c is minus 2. And by completing the square, we found that x was equal to a minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. Now quite often you'll see it written with one big division bar and just a 2a in the bottom. I don't like that way because it separates you from the idea that you had the axis of symmetry plus or minus this certain amount. You had the number that was in the middle between the two roots, And if you went to the left by some amount, this amount, you got to one of the roots. But if you were at that number in the middle and you went the other direction, you'd be at the other root. It's just like when we were looking at, 4 plus or minus, I forget what it was, square root of 11. Right? Same idea. Okay, so then, now, instead of having to complete the square on that original polynomial, the 6x squared plus x minus 2, I can just drop those numbers into this, and it's the same thing, right? I have the same solution. So I would have minus 1 over 12 plus or minus 1 squared minus 4 times 6 times a negative 2. We want the square root of that, and then it's over 12. All right, and that thing under the radical looks like the square root of 49, doesn't it? So square root of 49 is 7. So this is coming out as a minus 1/12 plus or minus 7/12. So then the two answers are 6 over 12 or a minus 8 over 12. So I'm getting that the roots are 1/2 and minus 2/3. But isn't that different from, didn't we factor this and get something different? There's our minus 2/3, but there's a mistake here?
Minus 1 and the other one 2.
I see it, yeah. Very good. 2x minus 1. And that fixes it. So then this wouldn't be a 1. The solution would be 1/2. 1/2 and minus 2/3. 1/2 and minus 2/3. So this is the quadratic formula. We need to, if there was going to be one thing in the course that we committed to memory, this is it. Does anyone, okay, so the discussion board is about this quantity, b squared minus 4ac. The discussion board is entirely about that quantity. It has a name. It is the determinant. I guess because it can determine for you what the quadratic what the graph is going to look like. And on the discussion board, you are going to discuss the 3 cases that could possibly happen for your discriminant. You see, anywhere on the number line, here's my number line, pick a point, you end up with a trichotomy. Numbers are either less than that point, they are greater than that point, or they are equal to that point. There's just 3 cases. And the point you're going to be interested in is the number 0. You're going to want to discuss what happens if b squared minus 4ac is less than 0. What happens if it's greater than 0? And what happens if it's equal to 0? And those are the 3 cases. So let's, and then they want you to come up with some example polynomials, some example quadratics for each case. And so I will produce some examples right now. Let's see. There's my 3 examples. And my claim is that I have all 3 cases here. Let's check b squared minus 4ac on these. For number 1, what do I get? Well, it'd be minus 2 squared minus 4 times 1 times, well, c is, what's c? 0. Okay. So it's looking like my b squared minus 4ac is just this number 4. In the second case, what do we get? Well, we'd have a minus 2 squared minus 4 times 1 times 1. And you get Is that the answer? How could I get the same? This was 4. how could this also be 4 if they are different? What does this second one compute to? It's 0. It's 0. Right, Rosalinda? This is 4 minus 4. 0. Okay, so I got a 0 on this one, that's strange. And then here in the third one,
Can you go to the first one?
go back to the first one?
Yeah.
Okay.
It's minus 2 squared, which is 4.
Yeah.
4 minus
4 times 1 times 0. 0 is the annihilator. That's the official name. It just demolishes anything it touches. It's gone. 0 times whatever is 0. So minus 4 times 1 times 0 is 0. It winds up saying 4 minus 0. Okay. But down here, we changed that 0 to a 1. Okay, and then on the third one, I'll have a minus 2 squared minus 4 times 1 times 2. And I get negative 4. So I really have done all 3 cases. And, but gee whiz, how did I get these examples like that so easily? You can do this too. It's not hard. So I started with this one. Does anybody see how this one factors? It's a perfect square. So this one factors like x minus 1 squared. If it was equal to 0, then that would mean we just have the one root. So if this thing was equal to 0, the only value for x that's going to solve it would be the number 1. How does this one factor? The GCF's not 1. That one factors immediately. So there's 2 solutions to that. If it was equal to 0, both the number 0 and the number 2 would satisfy it. This last one, though, not going to be so lucky. Right? It's going to cause a problem. Because, look, we figured out that this discriminant here came out to be minus 4. But that means that we would have a minus 4 under the radical. Well, that means it's going to be a complex number. So it doesn't have any real solutions. It will never solve the equation. There's no numbers x that satisfy this equation. So down here I had no solutions. Here, so on number 3 I had no solutions. How many solutions did I have on number 2? 1. And then up here on the first one I had 2. That's a pretty big hint to what's going on. And so, two solutions, one solution, and no solutions. Make the correspondence between two solutions and something about this number. Between one solution and something about this number. And no solutions and something about this number. What would your conclusion be?
One is less than 0 and the other is greater than 0.
And the third
Is equal to 0.
is equal to 0. So evidently, if the discriminant is going to be equal to 0, we're just going to have one solution. It'll be right on the axis of symmetry. Go back to the quadratic formula and look at it for a second. It says, if the discriminant was 0, it'd be the square root of 0 right here, which is 0. So it's minus b over 2a plus or minus nothing. Then the only root is just this number, minus b over 2a, because you're adding and subtracting nothing to get to the roots. However, if this is positive, if b squared minus 4ac is positive, then to get to the roots, you would start here, and you'd have to go to the right. You'd have to go to the right by this amount. You'd have to go to the left by this amount to get to the roots. You get 2 of them. But if this thing is negative, you can't even solve it. So it doesn't have any roots. That's the discussion board. It is to explain what is the discriminant, what is it doing, and what is the outcome. Provide your examples, show how they cover all three cases. Now, I like cute examples like this where everything, seems to just barely change, yet cover all the bases. So you also can construct such an example. Tell me one integer. What integer do you want? 3. You'll have one root here. The discriminant will be 0 on this one. But if I multiply that out, I could present it this way. I could just throw the 9 in the garbage. Now it'll have 2 roots. Or I could just drive that 9 way, way higher. Because remember, the curve is shaped like this, and if it's going to cross the x-axis, it is at those 2 points where it will, crosses the x-axis. Those are the roots. Those are the zeros, whatever you want to call them. They have a bunch of names. And so if I'm making a sketch here of the first one, x squared minus 6x, then this is 0 and this is 6. That's where it crosses the x-axis. However, right here on the axis of symmetry for this thing, you would find 3. And the one that just has the one root behaves like this. It just comes down and touches that 3. It just touches the x-axis in one place. Well, if I change that 9 to anything bigger than 9, then it will take that curve and move. If I changed it to a 10, it would be this yellow curve, but just moved up by 1 unit. So if I make my third example be x squared minus 6x plus 10, then it won't touch the x-axis at all, so it can't have any solutions. Well, then you've got all 3 cases. And then you could produce your 3 cases using your knowledge about where it has to cross the x-axis. And then, after the fact, say, well, look, the first one has a positive discriminant, the second one has a 0 discriminant, and this one's got a negative discriminant. And that's the whole argument. You get it? Oh, my session ended. So our solutions here were 1/2 and negative 2/3. Of course, knowing now what we know, we could have typed it in as the plus or minus version, but that had 12 and whatnot. Who cares? So, on to number 15. Let me say real quick, looking here in the instructions, they've got like some stuff that is weird. I have never seen them give a question where this was needed. This stuff about I is talking about complex numbers, and none of the questions we do use complex numbers. So you can pretty much ignore those instructions. 9x squared plus 24x plus 16. Last question. Let's use our quadratic formula. So, just to write it down one more time, it is that x is equal to a minus b over 2a plus or minus the square root of the discriminant over 2a. Okay, so A is 9, B is 24, and C is 16. So then x should equal to negative 24 over 18, plus or minus the square root of 24 squared minus 4 times 9 times 16 over 18. Well, then the hardest part of this becomes dealing with that square root. So is it really? So then that means that this original polynomial was a perfect square, because we saw already that if it was going to have a discriminant of 0, then it's got to factor like this. And in fact, since the answer is just going to be a minus 24 over 18, well, that's a minus 4 over 3. Right? So then, I could backtrack into what the factorization of this thing would look like. You know that it would have to have this as some of its terms. Because if I put the minus 4/3 in for x, then it would say 0. But this is not the factorization of that. Remember when we completed the square on ax squared plus bx plus c, we had to factor that a out front, and then we solved the thing that was remaining. So it would be the same thing that's going on here. This 9 would get factored out. So really, it really would look like 9 times this. And so 9 is just 3 squared. I could bring the 3 inside now. And that should, yeah, and that factors. That's our same polynomial. So even if you use the quadratic formula to get the roots, you have to still be careful about if you were going to use those roots to produce the factored form. That's it. Any questions? It's not a video this week, is it? All right, I will see you all in 2 weeks. 2 weeks. In week 9 is when I'll see you. And in that week 9,